Okay, and that's recording in progress. So just before we start, I would like to begin by acknowledging the traditional owners of the land on which we meet today, which we all meet today in various locations. And I would also like to pay my respects to elders past and present. And that's the start for us. So thanks for joining us tonight, everybody. Tonight our presenter is going to be Zac from previously from Project Bucephalus, the FRC team, and maybe even more notably at this point off of the Unqualified Quokkas, who are a robot in 3 days team that for the past season was ranked #1 in the world. So we're very excited to be hearing from Zac about sensors and control systems. And with that, I will turn this over to Zac. Thank you for joining us.
All right, thank you everyone for joining. Thank you, Mel. Yeah, I want to do a little bit about how, so you can Google about on the control systems wiki page about, all sorts of details, but I want to talk about how it affects your robot design. So also if you're very new to robotics, like getting you exposed to what's out there in terms of what sensors are available. So that's why this is called Practical Sensors and Control Systems. A little bit about me. I started first like a very long time ago, while I was very young, and I've carried that through. So hopefully you trust me to know sort of what I'm doing. I've been working in manufacturing sensors since 2022. So that's been really exciting, and it's been really good to see how that stuff translates from FRC into the real world. So we'll get started with what sensors and control systems are if you don't already know what they are. Sensors, you can think about it as how do you turn something about the real world into an electronic signal. So angles, distances, color, brightness, shape, sound, motion, those are all things that you can turn into an electronic signal. And they can be relayed into, for example, the RoboRio in different ways. So it can be a switch, so it can be on and off. It can be PWM, which is like an analog but more robust. There's CAN, which gives you a lot more power, and there's other buses that are available, outside of the FRC ecosystem that have other positives. Generally, though, in FRC, you'd probably just be sticking to the 3 switch PWM and CAN, maybe USB. Control systems can mean a couple of things. So a lot of FRC teams, they'll organize their team into a controls team. They'll handle the software and the electronics. The electronics is definitely a part of the control systems, and controls engineers are generally electronics engineers. Controls engineers also tend to do software, and there's a lot of software engineers that end up doing control systems. So electronics and software are entire disciplines within controls engineering. And there's also the control theory, which is the mathematics behind it. So when someone says controls to you, you can think of these 3 different things: electronics, software, and mathematics. And not only does it apply to the theoretical electronic and software parts of designing a robot, but actually it has a lot to do with the mechanical design. If you talk to a mechanical engineer, the best ones at making robots will have some understanding of control theory, because they'll know how to design a robot that is more controllable by software. So why should you learn control systems? Well, firstly, it broadens the kinds of robots you can make. We can look at the kind of progression of how complicated a robot can be based on how many sensors it has. So every bot, for example, is really super simple. You can have no experience and read the documentation and build one of these with basically no software at all. The robot that we built in January, this takes a little bit of programming, but it's actually very simple, and it allowed us to do some things that were a little bit special and helped, the driving, for example. And that was a big part of this robot being so successful, is taking some of the complexity from the mechanism into the software. So if you had to move this arm all by yourself with a single driver, it would be kind of difficult. but because of the sensors, it made it easier. 971 does things pretty differently. Their whole robot's actually designed around the fact that they can do complex control systems, like this lacrosse bucket. Like most teams wouldn't be able to do that because they wouldn't be able to control the lacrosse stick that precisely, right? Normally you'd have a flywheel, and it's very easy mostly to get a flywheel to spin at a constant RPM, but how do you model the arm to throw a ball really precisely? And it gave 971 an ability that no other team had, and that was being able to shoot with almost 100% consistency. Because throwing something has different dynamics to like rolling it out of a shooter. It also changes how you drive. So it's all well and good to have like your mechanisms kind of designed to be as large of a window as possible. We always talk about touch it, own it. You always want to make your robot, have as much leeway as possible in terms of how precisely you have to control it to pick up a game object. But when you have control systems that are more thoroughly designed, you can do things like what 1690 does, where they can shoot all the time, anywhere on the field, and the driver doesn't have to think about it. 254 as well. Their driver can simply press a button and the robot will go into a state where it's ready to score or ready to pick up. So it changes how you drive. It reduces the amount of cognitive load that a driver has when they're driving a robot. So they can actually drive a lot more effectively and think more about the strategy while they're driving than about the individual motions that they're making. And of course, autonomous. One really important thing to understand about autonomous is that, especially for certain games, winning the autonomous can actually have a big impact on the entire rest of the game. This is just a really cool spectacle of an example where autonomous can be really helpful. This is 971 from 2018. And you can see that the Red Alliance just barely got the advantage there, and they're going to hold that for the entire time until some other team comes in and places more cubes, and it puts them in advantage for the rest of the game. So depending on how your strategy goes for your game analysis right at the start of the season, your autonomous can actually be very important. And so investing your time into making the robot really good with sensors and control systems can be really valuable. So what are the goals of putting on your sensors? Because you don't just want to put sensors on for no reason, really. There's always going to be a reason. In FRC, it's going to be knowing where game objects are, it's going to be knowing where parts of the robot are, and it's going to be knowing where the robot is on the field. For example, where do you want to shoot to? Where do you want to pick things up? And that is called localization, and that's a whole subject in itself. So the first goal I'll talk about is detecting game objects. Like we talked about with how sensors and control systems let you, like they change the way you drive, detecting a game object allows you to drive faster in a sense. You're reducing your driver's need to depend on their reaction times, and they can just like drive straight through a game object, and you'll know that the robot will pick it up and control it. It's also good for autonomous. If you remember seeing in that video that I just showed you, the 971's robot, it'd actually wait until the box got all the way into the robot before it moved away. If it couldn't tell whether the box was in the clamp or not, then you'd have no chance of knowing whether you've actually grabbed the box, and then you could drive away without the box and then you wouldn't score. So detecting the game object is kind of an underrated thing, and it's a part of the Quokkas robot, and it actually allowed us to make the robot really simple so that for example, the rollers went straight into the shooter. if we can stop the rollers before it goes into the shooter, that means that we don't have to create an extra mechanism to stop the ring from going into the shooter. We can just control it via software with this little reflectometer. So that reflectometer we were talking about, that's Allen Bradley reflectometer. If we did it again, we'd probably use a beam break sensor. So this is where something, if something goes in between the two sensors, it'll break the beam and it'll send that back to the robo rear. The reason that's better than a reflectometer is because the signal to noise ratio is better. So with a reflectometer, you're sending out a signal and you're trying to get the reflection back. And that can be different depending on like the color of the material, what time of day it is even, the surrounding environment. A beam break sensor, you get all of the power of the light beam going straight into the other sensor. And so when that's blocked, all of that power is gone, rather than there being some noise left over in the ambient environment. So that's why beam break sensors are a lot more reliable, a lot easier to program as well. The one thing that you wouldn't use for detecting game objects is a limit switch. That's just because it has physical contact involved, and because FRCs, involves really big, heavy things smashing into each other. Limit switches are generally pretty weak. You can get strong ones, but they're generally pretty weak. So you want to avoid physical contact if you can, unless it works well with your mechanical design. Rotation sensors. So like I said, they can be useful for everything. Autonomous driving also helps with safety. So if you know what parts of your robot are where, you can stop it from colliding with itself. So if you have, let's say, a double jointed arm and it has to pass through a certain zone, you know that you can, if you know where the parts of the robot are, you can get it to avoid certain areas, and that's another value of the control system. We did it in the Unqualified Quokkas robot, so we could set the arm to specific heights. That also, we had a vision sensor on the front, so we could aim at different distances, and the driver wouldn't have to aim manually. The sensor allowed the motor to servo to a correct angle. Encoders are pretty ubiquitous in FRC. Any kind of rotating thing, you probably think about using an encoder first. But the types of encoders that you have can really change the way that you design the mechanism. So a capacitive encoder has a lot of precision. You can go really fast with it. These particular ones are a little bit bulky. And sometimes I found that you can get EMI issues occasionally. There's no reason not to use a capacitive encoder, but sometimes the accuracy can be actually way too high. And also it's generally only relative, not absolute. So what that means is if you start somewhere, it won't know where it started, whereas a magnetic encoder will always know exactly where it is. It won't have to reset. Does that make sense? I'll talk about an example that will make that more clear. Yeah, magnetic encoders are absolute. They can also be relative. Optical encoders, they can be either as well. You can get absolute ones, you can get relative ones. Because it depends on a physical disk, you'll also see that sometimes optical encoders are a little bit more bulky, but also they're generally more for industrial applications where the accuracy is actually really, really good, but the precision is not that high. Resolvers are a type of rotation sensor that probably is not used in FRC as often as maybe it could be. So the idea of it is that you have a magnetic field on two poles. And these poles are 90 degrees to each other. So you can, if this graph makes any sense to you, you'll know that depending on where it is, it'll give you a different return on the two poles. And that gives you a precise location on the rotation, no matter, basically it's an absolute measurement. So you're never going to lose track. So that's useful for swerve drive, because a swerve drive, you want to know that you're well calibrated and your 0 point's never going to change. You don't want to be influenced by magnetic fields as well, because inductive resolvers, even though they work with magnetic field, then they run at a high frequency, so they're not actually impacted by motors. So you can put a motor really close to an inductive resolver and it actually won't create interference with it. So this is actually a resolver I designed for the VexU robot for this particular swerve drive. And because it's so thin, that's another unique thing about inductive resolvers. They're very, very thin. You can also place them inside the wheel well, and you can create a very compact sensor. This arrangement is designed so that there can be like a slip ring that allows you to pass signals down through a continuous rotating mechanism. Often it would be a little bit more complicated to put on like a larger sensor. So that's the reason behind this. You can see it a lot in automotive because it's a fairly reliable way of doing it. And there are rangefinders, which are probably not so useful in FRC, but there are people that try to use it. So I'll start at the top. That's a triangulating rangefinder. It basically is similar to how like an Xbox Connect works, where it'll look for a dot, and the more left it is, for example, maybe the closer it is, and the more right the dot is, the farther away it is, just by triangulating it. That's an ultrasonic sensor. If you've done FLL, you probably know about it. It calculates the time of flight of a ping, kind of like sonar for a submarine. And that kind of time of flight concept gets expanded into LiDAR. So LiDAR, you have like a spinning laser, and it detects a time of flight. This is a time of flight sensor as well. With a spinning time of flight sensor, you can get a 3D map of your environment. There are some teams that have tried to use LiDARs to do localization, so finding out where the robot is on the field. That's very complicated. Project Bucephalus actually tried using an ultrasonic sensor to run along a wall. So that's another interesting way of using a rangefinder on a FRC robot, is that you can reduce the amount of load on the driver, and you can run along a wall at a precise distance at really high speed, much faster speed than what a driver could do. This rangefinder is more of a military one. Just for an example, you can range out to about 35 kilometers, and that's the kind of ability that a laser-based rangefinder can do. Those are all the slides that I had. So I'm open to getting any questions. Yeah.
Thanks very much, Zac. I've actually prepared my own list of questions because I run the electrical team on my team, but I know nothing about sensors. So I hope if you don't mind, I'll start with my questions, and they'll appear in the recording. And then if other people have questions, I can end the recording and we can go to those.
That'd be great.
Thanks. So I guess just on the slide that you have now, you sort of mentioned that rangefinders aren't super common in FRC. So like, what's the big problem that are preventing teams from successfully using rangefinders? Do you think it can be fixed, or is this just like not a good choice for FRC?
Yeah, so there's no reason not to use them as long as you're aware of what the limitations are. So LiDAR, obviously, you have a lot of data that you're handling. The only reason it's not used so much is just because of the amount of data that you have to process in real time, and then the robot has to decide what to do with it. Often you'll actually find that using cameras like, what's it called, Limelight. Limelight does all of that stuff for you, and you'll get other information like color, right? As well as distance to things. So that's why, this has been less valuable than cameras. When you're driving a car, it's a little bit more valuable because you don't necessarily care what color something is. You just care that you're not going to crash into it. In FRC, it's kind of a different story. Ultrasonic sensors, I said that Project Bucephalus tried it. You get a lot of noise in your data there. So you have to pay a lot of attention to filter that data out. And that noise can change depending on your environment, what kind of material you're passing up to, the humidity of the air, like the actual acoustic noise in the environment. It's actually really annoying. The angle that you're facing the wall at. So really it's like for the speed that you're running an FRC robot at, an ultrasonic sensor is probably not that valuable. LiDAR, not LiDAR, like a time of flight, infrared or visible light. They're a little bit better, but again, you don't get that much accuracy. So you couldn't position an elevator. You couldn't tell how high an elevator is because you'll have maybe a 15-centimeter error that you're not gonna.
So do you think for the applications that you would use a rangefinder for, do you think teams are better looking at a camera instead, like a Limelight?
Yeah, because the game design is generally going to be, if they want you to look at something, they're going to put like a QR code or an April tag next to it.
Yeah. Okay, thanks for that. I have a few more questions.
Yep.
So you mentioned that limit switches, well, basically you skipped past limit switches, but limit switches are something a lot of teams end up with basically through first choice. They seem to have an endless stockpile of them. Do you think there's any use for limit switches in FRC games? Can you give any examples of like a successful use of a limit switch?
That's a good question.
So I mean, we've tried to implement them in the past, and I think it's caused us a lot of difficulties. Either mechanically, something has gone past the limit switch and then basically broken the arm of the limit switch off, which is quite a good one. Or our really common mistake is that we'll wire them the wrong way, so they're normally open instead of normally closed, and that will cause some significant failure during a match. Do you think those
Yeah,
risks are sort of high enough that you're better off to avoid using them?
yeah. So I probably should have included the Hall effect sensor because Hall effect sensors are literally $5 and they do the same thing that a limit switch does. The only thing that people come across is that the switch point is not entirely defined. So that's probably the only advantage with a limit switch is if you really need a lot of precision to your location.
Yeah.
Generally, you don't need that much. Generally, a Hall effect sensor is perfectly fine and like literally $5. I can't see any reason to use a limit switch.
No, definitely. Like you were talking about, like elevator position earlier, we used Hall effect sensors on elevators where we didn't need to know precisely where it was. We just needed to know when it passed through. But I think it was 4 specific points. And for that application, we thought that Hall effects were really good. And then as long as you can get the magnet at the right distance, pretty easy to use as well.
Yeah, it's a good way of doing it so that you don't have to depend on an encoder, because elevators with like a string spool, that string can stretch And sometimes you actually want it to stretch a little bit, and sometimes there'll be a little bit of hysteresis. So actually having the sensor on the part that you're trying to measure the position of is a lot better than trying to measure it upstream from a long spring, basically.
Yeah, we've used a linear potentiometer in the past for our elevators, but the ones that we used were really expensive, like on the order of $300 or $400. So that makes it a bit hard to access. I've got another one, which is, and I think this will be applicable to a lot of teams. We build a lot of arms. Do you have a particular rotation sensor that you would recommend that teams use for arm positioning, like arm angle?
I try not to play favorites. Of course, I have ones that I'm particularly drawn to. So the Rev through-bore encoder, the half-inch hex through-bore encoder, was really easy to use when we used it on the Quokka robot. I generally try to avoid the magnetic encoders just because unless you can get the magnet well aligned, it's a little bit harder to use.
Yeah, I suppose for FRC teams, we just tend to use hex shaft for our axles. So the through bore, which suits the half-inch hex, is pretty suitable for most things.
Yeah, if the half-inch hex, if you are going to use half-inch hex, I would just recommend the Rev through bore encoder. If you're not using half-inch hex, so for example, if you're using, what's that, like, what's their spline that they came out with, a larger diameter spline?
Oh, I'm not sure of the name of that, but I know the one you're talking about. Yeah, you wouldn't be able to fit it in. Yeah, I think that's right.
So for something like that, I maybe would use an inductive resolver with a large inner diameter. They're kind of hard to find, but if you can use it, then I actually really like them.
Yeah, great. That's not actually something I've heard of before, so I'm interested to look into that one. And then I have one last question. I feel like all of my questions just relate to things I've messed up in the past, but like you've talked a lot about the sensors, but is there anything to watch out for when you're actually wiring sensors in?
Yeah.
Or any best practices around how to run wiring for sensors?
Yeah. I would read the documentation for CAN. It'll tell you exactly the best way to wire things up. So for example, when you twist the CAN wire, you know, there's actually a certain distance that the twist has to be. And then when you terminate them, you know, what resistance that has to be, and, you know, make sure that the lengths of the two wires are the same across the whole length of the thing. If you have stubs, which I don't think there's anything wrong with stubs. Some people might get angry at you for that, but if you have stubs, how long can they be? Make sure it's within a certain length, and really make sure that you get multiple people to check every single connection, because even if something looks like it's connected, you can't trust it, especially with CAN. If one line breaks out, it could like heck up your whole robot. So yeah.
How do you go about, like, if you know that you have or you suspect that you have a fault in your CAN bus, what's the best way to go about finding where it is?
So at least on Project Bucephalus, it's usually pretty obvious, because either like motor controllers will be flashing red at one part of the robot and not flashing red at the other part of the robot, or it'll be because like an arm has like crushed through some wires. It's definitely take advantage of the fact that you can talk to each of the motor controllers or devices on the CAN network, and you can go through each of the IDs. It can be helpful, for example, to write down what CAN IDs are what position in the daisy chain, so that, you know, you can find, I can talk to this one, I can talk to the next, I can't talk to the next one, so there must be a missing link in between. apart from that, you can use a multimeter and go and test things out.
Yeah.
I can recommend Wago lever nuts at least
as a connector.
Yeah, they're a little bit.
You might have to switch. I think you'll have to switch potentially which screen you're sharing with us, because I can see it on the projector behind you, but I can't see it on the screen. These are fairly common within FRC, I think, the Wago lever nuts.
Okay, Zoom isn't letting me do it.
It's all right. I've typed the name into the chat, so if anyone's interested, do you have a particular supplier that you'd recommend? Or just Google Wago lever nuts and see what turns up.
Yeah, I mean, this Element 14 just does them for $1 each, so it's not too bad. I'd probably avoid. I know it's like we want to be price conscious, but I would probably avoid getting like grey market connectors and things. We bought Anderson power poles, like PP45s from eBay, and they'd be like, a quarter of the price that you'd normally pay for them, but then they'd like melt. So
yeah, 100% agree. I think connectors, you want to buy the real deal.
Yeah, you can get away with not buying the expensive crimpers, I think, but at least for the connectors, like.
Yeah, for sure. One of the people who's watching has asked if you can explain, maybe in slightly simpler terms, what exactly a resolver does and how it works.
Yep. I can try, and you can let me know if I've done any better. Maybe I can get on the chair for this. This happens in Queensland. Safety doesn't exist here. So with a resolver, basically the goal is to get maybe don't have any markers. I would use the whiteboard. A resolver is just like an encoder, and it does a similar thing to what a magnetic encoder does. You have your primary axis, so that's how much magnetic field do you have in like the x-axis, for example, and the secondary, how much magnetic field do you have in the y-axis. And by knowing, for example, if it's down here, the magnetic field will be roughly equal. So you know that the position is at 45 degrees. It's the same thing that a magnetic encoder does. It'll get a magnetic field in one axis and a magnetic field in the other axis, and it'll tell you what direction the poles are. This is the same thing.
Right. So basically there's a magnet inside the part that's rotating, and then outside that there are a couple of sensors that can detect magnetic field, and then between all those sensors you're able to work out which way the magnet has rotated to, like what angle it's at.
Yeah,
is that roughly what's going on?
That would be a magnetic encoder.
Yeah.
The difference with a resolver is that actually you just have any kind of metallic or like conductive part, and your resolver stator will actually, it works like an induction cooktop where it puts current, which creates a magnetic field. So
it's like an electromagnet rather than a permanent magnet.
Yeah, exactly.
Okay.
And the advantage of that over a magnetic one is that because it has to run at a high frequency, so like 5 megahertz, for example, a low frequency magnetic field, such as the one that comes out of an electric motor, is not going to interfere with it. And you also you don't get the noise that's associated with the Earth's magnetic field or the the quality of the magnet that you're using. It's tightly controlled. So
Yeah.
yeah, that's a difference. It's rather than a permanent magnet, it's actually an electromagnet that induces the it induces a magnetic field in the rotor.
Yeah.
So, yeah.
Yeah, and so like the main advantage then, as you said, is that like with a magnetic encoder, mag encoders can pick up noise coming from other electromagnetic sources, and on robots there are just loads of those like the motors, but this one is, it sounds like, way more immune to that noise.
Yeah, that's right. So even things like the wiring, if you have high current wiring going through your robot, or if you have a big harness that bundles a lot of high current wiring, even that's not going to affect it.
Oh, that's really interesting.
Yeah,
That's
and
really
they can
interesting
actually
bit of technology.
they can be super precise as well. So let me get on my other chair. This, you can see how many antennae are on this resolver. That's because it's got several, I guess you could call phases. Basically, rather than dividing it up into, to a primary and a secondary, it's actually dividing it up into multiple. So it can actually tell, it's actually got all that precision divided down into a very small area, so it can tell what the position of it really accurately. So that's another.
What sort of resolution do you get? Like, is it to a nearest degree, or what are you looking at?
I would say within probably a 1/4000th of a degree.
Oh wow, that's
And
very accurate.
yeah, and the RPMs you go up to, I think I've been reading, it goes up to about 40,000 RPM, depending on your front end.
Okay, so that's, well, I mean, way faster than anything you'd see on an FRC robot.
Yeah, yeah. So it definitely has the performance for FRC.
Great. Well, thank you very much for explaining that. The the feedback I've got was that made sense pretty well. Thanks. So I think that was probably clear enough. I've run out of my own questions, so what I might do now is end the recording and then see if anyone else has any questions they would like to ask themselves. And just before everybody heads off, I will just pitch next week's session. So next week we are hearing from Dawood from EMU Robotics, and the topic for next week is actually going to be team sustainability. So a bit of a change, and I think it'll be really interesting to hear about that. But also a massive thank you to Zac for joining us tonight. I've learned some things. I hope everybody else has learned some things as well.